College Trigonometry, Chapter 9, Section 4, the inverse circular functions. Okay, for a one-to-one function, each x value corresponds to only one y value, and each y value goes back to only one x value. If a function is one-to-one, then it has an inverse. The domain of f is the range of the inverse, and the range of the function is the domain of the inverse. In other words, they swap out. So if AB is on a graph of f, then BA is on the graph of the inverse. The graphs are reflections of each other about the line y equals x. To find the inverse, what you do is you replace f of x with y, then you switch the x's and y's, and you solve for y. And then you go back and replace y with f inverse of x. Remember, that's not a power, it's the symbol for inverse. So the inverse sine function. Well, if you look at the sine function, if you apply the horizontal line test to it, the inverse is not a function. It's not one-to-one. So what we do so we can treat it as though it were one-to-one is we restrict the domain. For the sine, we restrict the domain to the interval from negative pi over 2 to pi over 2, and that gives us a one-to-one function. So in other words, if you look at this graph of the sine curve, when we define the inverse, we're going to restrict the domain to that blue part. It can only go from x equals negative pi over 2 to pi over 2. That will allow us to treat this as one-to-one. So the two ways of writing the inverse for the sine is you can do sine with the little -1, looks like a power, it's not. It means inverse. Or you can do y equals arc sine. Basically, that means that x equals sine of y for values from negative pi over 2 to pi over 2 for y. The domain for the inverse function is -1 to 1, which is the range of the regular function. The restricted domain of the sine is negative pi over 2 to pi over 2, which is going to be the range of the inverse. So for the inverse, the domain is -1 to 1, and the range is negative pi over 2 to pi over 2. We can think of y equals inverse sine of x as y is the number in the interval from negative pi over 2 to pi over 2, whose sine is x. In other words, x is the sine, y is the angle. Okay, and this is a graph of the inverse function. And you can see there the special angles from negative pi over 2 to pi over 2. And y in each equation. We're going to find the arc sine of 1/2 of -1 and -2. Pause the recording, give it a try, and resume to check your answer. Okay, so looking from negative pi over 2 to pi over 2 for a number whose sine is 1/2, that gives us pi over 6. So the answer is pi over 6. For b, writing the alternative equation, sine of y equals -1, y must be negative pi over 2. Again, looking for the number between negative pi over 2 and pi over 2, where our y value, our sine, is -1. C, there is no solution because there is no angle that gives you a sine of -2. Okay, to find the values with the graphing calculator, you're going to graph y equals sine inverse of x and locate points with x values of 1/2 and -1. So there's our graph, and it shows that when x is 1/2, y is pi over 6, which here, of course, you get the decimal equivalent. And then for -1, you see way over at the edge there, it's negative pi over 2. And again, for part C, there was no solution. It is tempting to give the value of the inverse sine -1 as 3 pi over 2, but 3 pi over 2 is not in the range of the inverse sine function. In other words, you've got to keep it to negative pi over 2 to positive pi over 2. Okay, the inverse sine function is increasing and continuous over its domain. The x-intercept and y-intercept are both 0. There's a little synopsis of our graph. If you want to pause and study this, do so, and if not, leave the recording running and we'll continue. Okay, now the cosine function, and again, we're going to restrict the domain, but this time to the interval from 0 to pi. If we restrict it the same as the sine, then it won't be a function. So it has to be different. So looking at it, here's what we're going to restrict it to, 0 to pi. And there's our inverse function for cosine. Again, it can be written as cosine with the little -1 or as arc cosine. Pause the recording, give it a try, and resume to check your answer. Okay, so for the first one, arc cosine of 1, again, we have to look for angle values between 0 and pi, and that's going to be 0. For part B, again, looking for 0 to pi, the only value that satisfies the arc cosine negative square root of 2 over 2 is 3 pi over 4. The inverse cosine function is decreasing and continuous on its domain. X-intercept is 1 and y-intercept is pi over 2. It is not symmetric with respect to the y-axis or the origin, and there's kind of what it looks like. Now the tangent function. We're going to restrict this domain to negative pi over 2 to pi over 2. And again, kind of the same idea, the x and y roles get reversed. This is the tangent function with our restricted domain. And there's the inverse function. Okay, so the arctangent, the domain is negative infinity to infinity. The range is negative pi over 2 to pi over 2. There's what it looks like. Notice we have those asymptotes there. It's increasing and continuous. The x-intercept is 0, as is the y-intercept. It is symmetric with respect to the origin and has horizontal asymptotes at plus or minus pi over 2. Okay, so for inverse cotangent, secant, and cosecant functions, for cotangent, we're going to restrict our domain to 0 to pi. For secant, it's going to be 0 to pi. And then for cosecant, it's going to be negative pi over 2 to positive pi over 2. So you got to kind of take note of those, which are restricted to which. Really, it's sine and cosecant that have the negative pi over 2 to pi over 2 and tangent. And then the rest are 0 to pi. Functions are formally defined with real number values. Sometimes we want the degree measured angles equivalent to them. And this just kind of shows you the intervals in the domain and everything that's involved there. So, and which quadrants we're talking about. All right, so find the degree measure for the following. Pause the recording, give it a try, and resume to check your answer. Okay, so the arctangent of 1, it's got to be, since tangent is from negative pi over 2 to pi over 2, that would be negative 90 to positive 90, and that's going to be 45 degrees. For the inverse secant being 2, again, we got to consider the restriction on our secant. Theta must be in quadrant 1, so it is 60 degrees. Now, you got to be really careful when you're doing these on your calculator. First of all, this inverse sine, cosine, and tangent are on the calculator. You hit the second button, and then you hit sine, cosine, or tangent. You must make sure you're in the correct mode. Cotangent, secant, or cosecant are kind of tricky because what you have to do, you have to remember that if y equals the inverse secant of x, then secant of y equals x means that it's 1 over cosine of y. So what you have to do is, if you want to find the inverse secant, you have to do the inverse cosine of 1 over the number. So if you want to find the inverse secant of 2, you have to do inverse cosine of 1/2. Okay, so it's a little tricky. For cotangent, you're going to do the same with tangent, and for cosecant, you're going to do the same with sine. Now, notice that since we take the inverse tangent of the reciprocal of x to find cotangent, the calculator gives values of cotangent in the same range as tangent, which is incorrect. So you'll have to adjust for there. So it is a little bit tricky. You do have to remember those ranges that we can use for the different trig y in radians if the inverse cosecant is -3, and find theta in degrees if arc cotangent is -0.3541. Pause the recording, give it a try, and resume to check your answer. Okay, in radian mode, you're going to do sine inverse of -1/3, and there's your answer. In degree mode, the calculator gives the inverse tangent values of a negative number in quadrant 4, but we need the quadrant to be 2. So arc cotangent of -0.3541 is going to give us, then we're going to have to add 180 to that. So it's about 109.4990544. Okay, now try these. These are a little bit tricky because what you need to do is you need to find the angle first and make sure you're in the right quadrant and all that good stuff. So pause the recording, give this a try, and resume to check your answer. Okay, so theta is the inverse tangent of 3/2. So in other words, the tangent of the angle is 3/2. And since it's positive, it's going to be in quadrant 1. So you could sketch a triangle for that, and you can solve to find that the hypotenuse is the square root of 13. And so the sine of the angle is going to be 3 over the square root of 13, or 3 square root of 13 over 13. For B, since our cosine is negative, that's going to be in quadrant 2. So notice we drew the triangle in quadrant 2, and we put in the -5 and the 13. We found that 12 is the missing side, and so the tangent is going to be 12 over -5. The optimal angle of elevation theta that a shot putter should aim for to throw the greatest distance depends on the velocity of the throw and the initial height. And here's one model, one way to figure out that angle. We've got a little bit of a diagram here. Okay, so suppose the shot putter can consistently throw a steel ball a height of 7.6 feet and a velocity of 42 feet per second. Use the formula that we just had on the previous slide. Back up if you need to write it down, and find the angle that will maximize the distance. Pause the recording, give it a try, resume to check your answer. Okay, so putting in all that information, and we're going to give the answer in degrees. We get a 90-degree angle. Okay, the rest of the recording is some practice. So pause the recording, give these a try, and resume to check your answer, and do this the rest of the recording.